All righty, let's go ahead and get started. So today we're going to continue our discussion of the Ramsey Neoclassical Growth Model. I think there's two main goals to discuss today. The first is I want to talk about or establish the equivalence in terms of the equilibrium outcomes of the Ramsey Neoclassical model we've been talking about and the optimal growth model solved by this kind of benevolent central planner that we discussed, I guess, a couple of weeks ago now. We'll then talk really briefly about some of the steady state properties of this model and the comparative statics, but I say briefly because if the equilibrium ends up being the same, then all the results that we've established in the optimal growth model should carry over identically to this model, and they do. The last part of class today, I want to start talking about the transition dynamics in this model towards a steady state. And in order to do that, we're going to have to develop some new concepts one is called a phase diagram, which helps us think about the equilibrium path of consumption and capital as we approach the steady state. And then we should be able to finish up this section either by the end of class on Wednesday, or possibly it might bleed over into next Monday. So we still have your test on schedule for next Friday, right? Nick Glenn is going to administer your test, but then he has a conflict during the time in which it's due. So you guys will just be on the honor system to hand in your test at the 3-hour limit, either to him or in his office, or you can put it under my door, okay? All right, so let's go ahead and get started then. What did I write down before class began? So the first two equations here are the two equations that characterize the equilibrium in the optimal growth model. You will notice that there is this intertemporal Euler equation, right, where we have substituted out consumption from the model. So the Euler equation is a second order difference equation in the capital stock, followed by a transversality condition. That's the other key optimality condition in that model. The Ramsey model equilibrium is characterized by these set of equations, right, where in this case, I'm characterizing the equilibrium over sequences of consumption, capital, the return to capital, and the real wage, or the return to labor. So we've got a Euler equation for consumption, a period by period flow budget constraint, where I've made one simplifying assumption, recognizing that household assets must equal the capital stock every period. I've just substituted all places where there's an A for K. The return to capital, the return to labor, and then what is this last condition? This is the strong form of the no-Ponzi-game condition. These are the set of equations that characterize the equilibrium in the Ramsey model, okay? This leads us then directly to what I have in my notes is labeled as proposition 1. So I'll read it and then we'll go through the sketch of the proof together. In the Ramsey model, if we assume that the production function is neoclassical, and we assume that utility is also neoclassical, so increasing, continuously differentiable and concave, and also that we have proper discounting in the model, meaning that rho exceeds the population growth rate, the equilibrium then is Pareto optimal and actually coincides with the optimal growth path, maximizing the utility of the representative household, okay? Or another way of looking at it is saying that the Pareto optimal equilibrium in the growth model can be decentralized into a competitive equilibrium. So the two models should be equivalent, or should generate equivalent outcomes. Now, how are we going to prove this? Well, there's two steps. We need to prove that the Euler equation from the optimal growth model is equivalent to the Euler equation from the Ramsey model. But that's not sufficient. The other thing we have to prove is that the transversality condition from the optimal growth model is equivalent to the no Ponzi gain condition. If we can establish that, then the two models have to be the same in equilibrium. Okay. The first thing that I want to make clear is that there is no, you guys will recall there's no population growth in the optimal growth model, right? So we're going to set n equal to 0 in the context of the Ramsey model for this proof only, and then we'll reinsert it afterwards. All right, so obviously they're only going to be equal in the special case in which there's no population growth. Or alternatively, we could have put population growth back in the optimal growth model and they would have turned out the same. Okay, so let's first look at the Euler equation. You'll notice here that consumption is equal to 1 plus RT times KT. Well, what is RT? According to the firm's optimality condition, it's 1 plus F prime of KT minus delta times KT plus the real wage. Well, what's the real wage? It's F of KT minus KT F prime of KT, and then minus a 1 plus n times KT plus 1. And if n is equal to 0, it's just a minus KT plus 1 then. Now, some of this stuff looks like it should cancel. Notice there is an F prime of K times a K and a minus F prime of K times a K. So that's gone. And we are left with, let's see, F of KT plus a 1 minus delta KT minus a KT plus 1. Now, if we stick that into the Euler equation then, in the Ramsey model, we get U prime F of KT plus 1 minus delta KT minus KT plus 1 is equal to 1 over 1 plus rho times U prime of CT plus 1. It's F of KT plus 1 plus 1 minus delta KT plus 1 minus KT plus 2 times a 1 plus RT plus 1. Well, that is a 1 plus F prime KT plus 1 minus delta. So that's what the Euler equation simplifies to then in the Ramsey model. Now, if you recognize that n is equal to 0, then what is 1 over 1 plus rho equal to? That's the same as beta from the optimal growth model. And you'll notice then that the Euler equation is identical to the one from the optimal growth model. There's absolutely no difference between those two. And so the path of consumption over time governed by the Euler equation in the Ramsey model is equivalent to the path that governs consumption over time in the optimal growth model. So for a given initial consumption then, the ensuing path of consumption for the two models is exactly the same. Okay, what about the no Ponzi gain condition or the transversality condition? What we want to do is we want to show that the transversality condition in the optimal growth model, which says that the limit as t approaches infinity of beta to the t u prime of ct times f prime of kt plus 1 minus delta times kt equals 0. We want to show that that implies or is equivalent to the no Ponzi game condition right here. All right, well, we know from the Euler equation in the Ramsey model that u prime of ct plus 1 is equal to 1 plus rho over 1 plus rt plus 1 times u prime of ct. Or alternatively, that u prime of ct is just equal to 1 plus rho over 1 plus rt times u prime of ct minus 1. If I just scroll the Euler equation back one period. Now, hopefully you guys remember, it was either from the last class or the class before, I don't recall, that if we were to scroll this equation back again and substitute the result into u prime of ct minus 1, and then scroll it back 2 periods and substitute it in for ct minus u prime of ct minus 2, and we do that repeatedly, what you're going to find is that eventually can be written as the product from j is equal to 1 to little t of 1 plus rho over 1 plus rj times u prime of c0. In other words, we can scroll the Euler equation back all the way to the initial period in a way that expresses today's marginal utility of consumption as some discounted value of the marginal utility of consumption at date 0. Well, what's that equal to? If I expand that product, looks like to me it's 1 plus rho to the t, right? There's lowercase t terms here in that product, times a 1 over 1 plus r1 times 1 over 1 plus r2, all the way out to a 1 over 1 plus rt. Now let me employ a little trick here. I'm going to multiply and divide by 1 plus r0 over 1 plus r0. That does not change the expression for the marginal utility of consumption, times u prime of c0. Now, because n is equal to 0, what does 1 plus rho equal? That's beta inverse, right? So 1 over beta to the t times, let's see, if I shove one of these 1 plus r zeros into this product, we get the product from j is equal to 0 to t of 1 over 1 plus rj times 1 plus r0 times u prime of c0. All right, now let's use this expression to evaluate the transversality condition. So this would be the limit as t goes to infinity of beta to the t. Now what is u prime of ct? It's this expression here. That's 1 over beta to the t, product from j is equal to 0 to t of 1 over 1 plus rj, 1 plus r0, u prime of c0, times f prime of kt plus 1 minus delta, all of that times kt, and the transversality condition is such that that limit expression is equal to 0. Okay, you'll notice that beta to the t should cancel with a 1 over beta to the t. I can take these terms that are independent of t and move them to the outside of the limit expression. And since this whole thing is equal to 0, I can divide by both sides and they go away. And you're left with limit as t approaches infinity of kt times the product from j is equal to 0 to t of 1 over 1 plus rj times this term here, which you'll notice is just equal to 1 plus rt. This 1 plus RT should cancel with the final 1 over 1 plus RT in this product term. So the whole thing could then be written as the limit as t goes to infinity, kt times the product from j is equal to 0 to t minus 1 of 1 over 1 plus rj is equal to 0. And what does that equal? That is the no Ponzi game condition. So the transversality condition implies the no Ponzi condition and vice versa. So not only is the key intertemporal condition in the two models equivalent, but the key terminal value condition or the asymptotic condition is equivalent in both models. Therefore, the allocations that emerge in the two models, starting in date 0 to infinity, provided they have the same initial condition, are going to be the same. Absolutely identical. The result, I don't think, is all that surprising, right? The Ramsey model satisfies all of the conditions necessary for invoking the first and second welfare theorems of microeconomics. First and second welfare theorems of micro. There are no distortions, there are no frictions. Markets are perfectly competitive, information is perfect, and so the Pareto optimal allocations should be consistent with or supported by, I should say, a particular decentralized competitive equilibrium. Adam Smith's invisible hand principle is going to apply in this model. If everyone behaves optimally, we're going to reach the first best social outcome because all markets are perfect in this case. Now, obviously, that doesn't describe the real world, right? There's plenty of, most of the research in macroeconomics today incorporates all kinds of distortions and frictions in them that make them interesting and usable to address certain policy issues today. But in this basic workhorse model, there is equivalence between these two models because none of those distortions are present. The implication then is that all of the properties concerning the steady state equilibrium, its uniqueness, its existence, its stability in the long run, should also carry over to the Ramsey model. If the equilibrium is equivalent and they start from the same initial point, then all of those properties in the optimal growth model should carry over identically to the Ramsey model. Questions? Nothing? Okay. Let's talk about the steady state for a few minutes before we discuss transitional dynamics. Just like in the solo growth model, just like in the OLG model, under certain conditions, and the optimal growth model, the steady state equilibrium is going to be defined as an equilibrium path whereby eventually the capital stock is going to converge to some fixed point, and consumption is going to converge to some fixed point for all t bigger than or equal to cap t. So cap t is this point out in the future at which the economy reaches a steady state equilibrium. Okay, ladies and gentlemen, you guys should be able to tell me, or at least be able to characterize how to find the steady state equilibrium here. All right, what conditions do we need to appeal to if I want to find out, if I want to characterize what K star and C star are equal to?
Assumptions 1, 2, and 3.
Sorry?
Did you like assumptions 1, 2, and 3?
Well, that's to prove the existence of, right? But if I just want to find what the steady state is, characterize it. In other words, write down the set of equations that essentially defined what the steady state is in this model.
Transversality.
Well, you need the Euler equation and you need the intertemporal budget constraint, right? So remember, what is the Euler equation here? It's u prime of ct is equal to 1 over 1 plus rho u prime of ct plus 1 times 1 plus rt plus 1, which is f prime of kt plus 1 plus 1 minus delta. That's one of the equations. The other key equation in the model is, of course, this period by period budget constraint or solvency condition, however you want to call it. Its consumption is equal to output plus whatever capital is left over after depreciation minus 1 plus n times kt plus 1. So by the way, here I'm going to reinsert population growth into the Ramsey model without loss of generality. Okay. The steady state has to hold along an equilibrium path for all t bigger than cap t, meaning that it must be satisfied by these two equations. Or maybe I should say it more clearly, these two equations are going to hold for all t, including once the economy reaches the steady state. Okay, so how do we find the steady state? Plug in the steady state values into these two equations. This becomes u prime of c star is equal to 1 over 1 plus rho u prime of c star times f prime of k star plus 1 minus delta. This is a basic skill that you guys have to have. Excuse me. You've got to be able to write down the optimality conditions and then find the steady state conditions that come from them. Not being able to do this won't get you through the class, I promise. You got to be able to do this. Okay. Where do we go from here? The marginal utility of consumption is non-zero, so that cancels. And we can find that the marginal product of capital at the steady state then has to be equal to 1 plus rho minus 1 plus delta. The ones cancel and we get that f prime of k star is equal to rho plus delta. So if a steady state value of capital exists, which we know it does, it has to satisfy this equation. F prime of k is equal to rho plus delta. This, by the way, is exactly the same as the one we found in the optimal growth model. Remember, in the optimal growth model, we found that f prime of k was equal to beta inverse minus 1 plus delta. Well, what is beta inverse? That's just 1 plus rho divided by 1 when n is equal to 0, right? Minus 1 plus delta. Cancel, cancel, rho plus delta. So it's the same thing. It's exactly the same equation. What's the steady state value of the real interest rate? That should be equal to f prime of k star plus 1 minus delta, right? R is equal to f prime of k plus 1 minus delta. So R star should be f prime of k star plus 1 minus delta. Well, what is f prime of k star equal to? Rho plus delta. plus 1 minus delta. No, that's not right. Is that right? No. Rho plus delta. I don't have that right. Hold on. Why do I have this? Y'all,
Should have a 1 there.
yeah, and there's no 1 there. I'm thinking of the gross interest rate, not the net. F prime minus delta is RT is equal to F prime of KT minus delta. So F prime K star is rho plus delta and then minus a delta, which means that R star is equal to rho, right? So the real interest rate, real return to capital in the Ramsey model is exactly equal to the discount rate. Now, why is that interesting? You will recall that assumption 2, I believe in this chapter, was that the discount rate had to exceed the population growth rate, correct? Well, this implies then that the steady state real interest rate must exceed the population growth rate. And so in the Ramsey model, and I think I pointed to this or touched on this a little bit in the last class, is going to avoid the dynamic inefficiency that emerges from time to time in the OLG model. The capital stock is never going to get so big in equilibrium that the real return to capital is less than the population growth rate. So you will not see dynamic inefficiency in the Ramsey model like you did in the OLG model under some conditions. You guys see how I got that? I'm just finding the steady state value of the real interest rate. It's equal to F prime of K star minus delta. Well, F prime of K star is rho plus delta, so R star has to be equal to rho. And because rho is bigger than n by assumption, then that means R star is going to be bigger than n. So there's no dynamic inefficiency. That also will imply that the transversality condition should hold along the steady state, right? The limit as t goes to infinity of kt times the product from j is equal to 0 to t minus 1 of 1 plus n over 1 plus rj. What is that equal to at infinity, where we've reached this steady state? It's k star times the product from j is equal to 0 to infinity of 1 plus n over 1 plus r star, correct? Well, the only way this thing is equal to 0, which is what the transversality condition says, is going to be what? That will hold as long as r star is bigger than n, right? Or alternatively, if k star is equal to 0, but we know there's going to be a unique steady state value of k with positive economic activity. So the only way the transversality condition or the no Ponzi game condition holds in the steady state is if r star is bigger than n. And we know that's going to be true because that follows from assumption 2, that rho is bigger than n. What is the steady state value of the real wage here? Well, that's just f of k star minus k star times f prime of k star. That'll be some finite value. And then we can find the steady state value of consumption as f of k star. We just find that by appealing to the period by period budget constraint. So it's c star is equal to f of k star plus 1 minus delta k star minus 1 plus n times k star. And then of course, some of this cancels. The ones cancel and you're left with f of k star minus delta plus n times k star. So again, if a steady state value of consumption exists, it has to satisfy this equation. That's what I mean when I say things like characterize the steady state on an exam. Derive the equations that are consistent with the steady state, this and this. Now, I'm not going to prove this, but proposition 2 says that in the Ramsey growth model, with all the assumptions, blah, 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 there exists a unique steady state capital to labor ratio, which satisfies this equation, and a unique steady state consumption, which satisfies this equation. How do I prove that there exists a unique value of k star? How do I prove that? How do I know there's only one finite value of k star that satisfies this equation right here?
So we can take the same approach that we did in the solar model and the OLG model. So we can take a limit and then use the intermediate value theorem to show that only one value exists. And then we can take the derivative to show that the function is decreasing.
Because of the Inada conditions, we know that f prime is huge for small k, and we know it's 0 for large k. We also know that it's continuous, and that because its f double prime is negative by assumption, it's strictly concave, that the graph of f prime is strictly decreasing. Rho plus delta is just some positive number. So just like Tavoy said, by the intermediate value theorem, there must exist some k star between 0 and infinity, such that f prime of k star is equal to rho plus delta. The proof is exactly the same as the solar model. In fact, it's even easier, really. Proposition 3 concerns some comparative static results. Imagine we transform the production function to look like this, a f tilde of k, so that we can reinsert technology into the production function. Let's do some comparative statics, but I don't want to do any math. I want to just draw the pictures. What's the partial of k star with respect to A? The partial of k star with respect to rho, partial of k star with respect to delta, and the partial of k star with respect to n. What are those comparative statics equal to? Well, let's do this one at a time and just do it on the graph. What if there's a positive shock to A so that technology is now higher? What's going to happen on our steady state graph over here? This whole thing is going to shift out, right? And as a result, the steady state capital stock should rise. So dk dA should be positive. I would encourage you to go and derive that analytically using calculus. What about dk d rho? What if rho gets larger? What happens to the steady state value of capital? It's going to decrease because this line here is going to shift up, causing us to move not from here to here, but from here to here. So dk d rho should be negative. What if there's an increase in the depreciation rate? What happens to the steady state value of capital? Exactly the same thing. And in fact, delta enters the steady state condition in exactly the same way that rho does. And so in fact, the comparative static should be identical. It should be equal to dk d rho. How does an increase in the population growth rate affect the steady state here?
Does it? I don't think it does.
It's 0.
We assume it's 1
Hmm?
in the beginning. The assumption that we made that the labor force is 1.
Nope. Nope. This is one difference between the Ramsey model and the Solow model. Now, in the optimal growth model, I think we presented that model assuming 0 population growth, if I'm not mistaken. In the Solow model, what happens when there's an increase in the population growth rate? Think graphically. That break even, or I'm sorry, the depreciation plus population growth schedule shifts up, which causes the steady state value of capital to shrink. In this model, an increase in the population growth rate doesn't affect the steady state capital stock at all. That's one interesting difference between the Solow model and the Ramsey model. Population growth impoverishes nations in the Solow model. It has a neutral effect in the Ramsey model, at least on the capital stock, I should say. Let me be clear about that.
Well, which is more realistic? Like, does the population actually make people worse off? Population growth?
Well, what do you think?
Yes.
I would say it depends. I think for long run growth, you need population growth because one of the biggest sources of technologies comes from people. You can't really invent new technologies unless you have smart people developing those technologies. So from that case, I mean, humans are our most valuable assets, right?
If they're not smart people.
Well, take a sub-Saharan African country where population growth rates are considerably higher than they are in the developed world. One could argue that if those countries could adopt public policies that could reduce population growth rates, that per capita incomes would be higher. So to that point, I think there is some truth to it. Remember, these are just models. They're not the truth, right? It's likely if you were to do a rigorous empirical study, you would likely find that some population growth is important for a robust growing economy. But beyond some certain point, it starts to be more of a drain on resources. So it's probably kind of hump shaped. But the two models generate stark differences in their conclusions. The Ramsey model says that it doesn't affect the steady state capital stock. The Solow model says that it reduces it unequivocally. How about, let's do one comparative static for consumption, just to say we covered it. What if I wanted to, so remember, C star is equal to F of K star. Well, let's say A times F tilde of K star minus delta plus N times K star. Obviously, population growth does affect steady state consumption in the Ramsey model. It just doesn't affect the capital stock because N shows up in this consumption equation, right? What is what's the partial of C star, let's say, with respect to A equal to? Let's do that comparative static. Well, that would be what? F tilde K star plus A F tilde prime of K star times dk star dA minus delta plus N times dk star dA. If I group terms here, it would be F tilde of K star plus dk star dA, which we know is positive, times A F tilde prime of K star minus delta plus N. What's the sign of this? Positive plus a positive times a positive minus a positive. But be careful. What's A F prime K star equal to? Rho plus delta, right? We know that from the steady state condition. Rho plus delta minus delta plus N is just rho minus N. What is the sign of rho minus N? It's positive by assumption 2. Remember, rho has to be bigger than N. So it's a positive plus a positive times a positive means that dCdA is strictly greater than 0. You can sign all of the comparative statics for consumption by appealing to this assumption here, that rho is bigger than N. But you have to substitute out F prime of K minus delta plus N, or you have to substitute out what F prime of K star is in the steady state. What about dC star dN? How does consumption change with an increase in the population growth rate? Well, that's going to be what? A F tilde prime K star times dK star dN minus K star minus N times dK star dN. Fortunately, we know that dK star dN is equal to 0. Population growth has no impact on steady state capital. So dC dN is just minus K star, which is negative. So Ben, whereas population growth doesn't have any effect on steady state capital in the Ramsey model, it does lower per worker consumption. So in that sense, it does still impoverish people on a consumption basis, but not in terms of the economy's capital stock. Okay, so to sum up what we know about the steady state, I think there's 3 results here relative to the Solow model concerning comparative statics in the steady state. One, it's the discount rate rho, not the exogenous savings rate, that affects the rate of capital accumulation, right? In the Solow model, one of the most important factors that determines the steady state capital stock was the economy's savings rate, exogenous savings rate. The economy saves more of its resources, capital accumulation rises in the long run. In this model, savings is endogenous, but it's sort of related to the discount rate. In what sense? If the discount rate is higher, rho gets bigger, then agents discount future utility more. They become more impatient and they want to consume more today and save less. So as rho goes up, steady state capital declines. Or if they become more patient in the sense that rho is declining, steady state capital will rise. So the discount rate is sort of related in an endogenous way to your willingness to save over time, because it tells you how much you essentially penalize future consumption relative to near-term consumption. Number 2, population growth has no impact on steady state capital in the Ramsey model, but it has a negative impact in the Solow model, which we've already talked about. Number 3, there is another similarity here, that between this model and the optimal growth model is that you'll notice that steady state capital and consumption do not depend on specifics regarding the utility function. The only thing regarding preferences that affects the steady state in the Ramsey model is the discount rate. But whether your utility function is logarithmic or CES or whatever, doesn't affect the steady state, right? The utility function is only useful basically for ranking consumption bundles. It doesn't matter what that particular, what numbers you assign to that ranking, okay? Now, let me just warn you, if you augment exogenous technological growth to this model, then I believe the utility function will matter for the steady state, because consumption per worker is going to grow then at a fixed rate even in the steady state. And so to find the steady state value of consumption per effective worker, it's going to depend on the growth rate, which feeds through the utility function, and therefore will have an impact on consumption per worker in the long run. But you should work through that model with exogenous technological growth to verify that. In fact, if I'm remembering this right, the technological growth rate combines with the population growth rate in a particular way to define the what's called the effective discount factor. So this assumption that rho has to be bigger than n is modified when you have technological growth. It's something like rho plus g minus rho times g has to be bigger than n, something like that. It's some combination of rho and g there that has to be larger than the population growth rate. I'm sorry, yes, larger than the population growth rate in order for the utility function to have proper discounting, for beta to be less than 1. So there should be a review question there that reinserts technological growth into the model, but it's all still perfectly solvable. Most of the main results carry over in kind of an isomorphic way. Okay, any questions then about that before we change directions here? Well, that's pretty clear. The last topic that I want to discuss in the context of the Ramsey model then is the transition dynamics. Okay. Again, one of the reasons why we talk about the solo model in the first couple of weeks of the class is because I like to constantly make comparisons throughout the semester to what actually happens in the solo model. It provides a way to make more sense of these more complicated models. In the solo growth model, how did we, or what condition was necessary in order to establish the stability of the steady state? That is, that all paths led to the unique steady state.
Monotone convergence.
Well, that's kind of just another way of saying stability. But what mathematical condition was necessary in order to establish that?
Well, the gradient must be less than 1.
The mapping from K. So remember the solo model, the key equation that governs how the capital stock evolves over time is this fundamental law of motion, which shows how KT plus 1 is a function of KT. That is a first order difference equation. It was a nonlinear difference equation, but as Tavoy rightly says here, that the key to stability is basically the slope of that mapping in a neighborhood of the steady state. At least for local stability, that is, if you start within a neighborhood of the steady state, you'll always converge to the steady state if the gradient of that mapping is less than 1 in absolute value, okay? Things are no longer as simple in the Ramsey model because we can't derive a first order difference equation for KT plus 1 in terms of KT, right? What we really have are two equations that govern the evolution of KT and CT simultaneously. Now we could combine them and we get a second order difference equation in the capital stock, but that doesn't that doesn't carry over. The results from the solo model cannot be applied directly to that model. Okay, we've got to develop a new notion of stability in a model that has both states and controls, where we've got to think about two equations simultaneously as these two variables, both the state and control, evolve towards the steady state over time. Okay, let me rewrite the two main equations. I'm going to label them 1 and 2 of the Ramsey model, because I'm going to come back to these equations over and over again in discussing the stability or the transition dynamics implied by this economy. So first we have the Euler equation. And secondly, we have the period by period budget constraint, or since we're substituting assets and real interest rates and wages out of the equation, it may be more appropriate to think of it as a solvency condition or even a resource constraint. It's 1 plus n times kt plus 1 is equal to f of kt plus 1 minus delta kt minus ct. So these two equations, in concert with the no-Ponzi game condition, constitute basically the equilibrium of the Ramsey model, okay? For a given initial value of capital. Okay. The combination of boundary conditions, both at 0 and at infinity, where the boundary condition at infinity is the transversality condition, essentially, is typical for economic problems that involve both states and controls. Okay, this is a different type of model than the solo model, right? There really was no control in the solo model. The capital stock evolves more or less exogenously as a result of savings and depreciation. The appropriate notion of stability in these types of models that have states and controls is what's known as saddle path stability. That's the concept that I want to talk about for the rest of class today. Okay. Now, I touched on this a little bit in the last class, or perhaps the one before, I don't recall. But you will recall, hopefully, that the consumption level, of course, consumption is the control here, whereas the capital stock KT is the state. And ignoring the no-Ponzi condition, equations 1 and 2 don't pin down a specific value of initial consumption, C0. In other words, 1 and 2 imply that initial consumption is more or less a free variable. Okay, this is common in models that have these types of states and controls. So initial consumption has to adjust or jump to satisfy the transversality condition or the no-Ponzi condition at infinity, right? We talked about this, I think, maybe it was the last class, right? The Euler equation determines the path of consumption from period 1 to infinity for a given value of initial consumption. But to determine the optimal value of initial consumption, we have to appeal to the transversality condition. And what is another way of equivalently stating the transversality condition? It's that the family's lifetime budget constraint binds in equilibrium. Remember, this period by period trading environment in this model needs to be equivalent to the period date 0 trading Arrow de Brue environment, right? Where the proper budget constraint is a lifetime budget constraint. So C0 is chosen optimally to ensure that the subsequent path of consumption over time will fully exhaust the family's lifetime budget constraint. That is, satisfy the transversality condition. So C0 jumps immediately onto that path that will eventually take the economy to satisfying the lifetime budget constraint in the long run. Okay. Because C0 jumps to that path then, or is free to jump in the initial period, stability requires the existence of a one-dimensional object in capital consumption space. Okay, that one-dimensional object or curve tending towards the steady state is what's called the saddle path, right? When we analyze stability in the Solow model, we could look at how KT plus 1 was related to KT. Here, we've got two variables that we have to track simultaneously. Okay, the saddle path is this unique one-dimensional object in capital consumption space, such that for an initial value of capital, your initial value of consumption is going to jump up to some point, at which point consumption will evolve over time until you reach the unique steady state found in the last proposition. Okay, now fortunately, the economic environment that we're working in here ensures that this saddle path actually exists and is unique. And in the next class, we're gonna prove its existence and uniqueness formally. Okay, what I want to try to do today is characterize what that saddle path looks like informally. All right, and I want to do that using something called a phase diagram. I think the phase diagram is a useful conceptual device that can help us understand the joint dynamics of capital and consumption in this model, and can help you visualize what the actual saddle path solution looks like. Okay, we're going to develop a phase diagram by appealing to equations 1 and 2 in capital consumption space. And we're actually going to find that equations 1 and 2 will help us demarcate regions of capital consumption space that shows us what regions of that space lead to unstable values for those two variables versus regions that lead to stable values for those particular variables. Okay, and again, let me just emphasize this, that the phase diagram shows us all the possible optimal paths for K and C given an arbitrary initial value of C0. The phase diagram, in other words, doesn't tell us what the optimal C0 is. For that, we've got to find the saddle path solution. Okay, so every trajectory that we're going to derive using our phase diagram is fully consistent with equations 1 and 2. Only one of those trajectories, however, is consistent with 1, 2, and the transversality condition. That's the one that is optimal, and you might imagine that is the saddle path trajectory. It leads directly to the steady state. That's probably a bit difficult to wrap your brains around. So let's just show exactly what this leads to. Just got 15 minutes left. Okay, I should be able to get some of this done. Let's first think about capital dynamics in the Ramsey model. Okay, I'm going to draw a graph over here, which is going to start my phase diagram. It's going to be capital consumption space. So capital on the horizontal axis, consumption on the vertical axis. Okay. I want to find, so here's what I want to do. I want to find every point in this quadrant that is consistent with, let's say, the capital stock rising over time. Can I locate regions of KC space such that the capital stock is, we know, is growing from one period to the next? Sure we can. Okay, if KT plus 1 is bigger than KT, then KT plus 1 minus KT has to be bigger than 0, correct? All right, what's KT plus 1 equal to? Let me appeal to equation 2 on my last piece of paper. I can solve for KT plus 1 as a function of KT and CT directly from equation 2. What is it equal to? It's equal to 1 over 1 plus n times f of KT plus 1 minus delta KT minus CT minus a KT is bigger than 0. Let me express CT then as an inequality with only KT on the right-hand side. So multiply both sides by 1 plus n. You get f of KT plus 1 minus delta KT minus CT minus 1 plus n KT bigger than 0. So CT is going to be less than f of KT. Let's see, some of this cancels. Minus delta plus n times KT. There you go. Okay. What this inequality shows us is that there is a locus of combinations of KT and CT that are consistent with the capital stock being stable from period T to T plus 1. Right? Imagine for a moment that CT is equal to the right-hand side. Well, you just reverse this, and that's the point at which KT plus 1 is equal to KT, right? Well, let's graph that locus of points. It should look something like the following. This is what I'm going to call the KT plus 1 is equal to KT locus of points. Every combination of KT and CT on this curve is consistent with KT being stable over time. In other words, the capital stock is not changing, right? Now, if CT happens to be less than the right-hand side, in other words, we're at a point somewhere inside or underneath the locus, then what is happening to the capital stock over time? It's getting bigger. KT plus 1 is bigger than KT. So the capital stock is moving to the right. KT plus 1 is going to be bigger than KT. Any point that is above this locus is going to be one in which the capital stock is therefore shrinking over time. Any point along this locus is one in which the capital stock is not changing between T and T plus 1. Now you will notice here that the level of consumption that is consistent with stable capital over time is increasing in the capital stock up to a certain point. And then it starts to fall, right? What is that point? Well, the locus of points here is C is equal to f of k minus delta plus nk. So the level of consumption consistent with stable capital is rising up until the point at which f prime of kt becomes less than or equal to delta plus n. You guys recognize that? the point at which f prime of k is equal to delta plus n is the so-called golden rule capital stock, right? That's kg. Any value of capital greater than the golden rule is going to have consumption falling. That is the level of consumption consistent with steady capital. So be careful about the interpretation there. How about consumption dynamics? Let me do the exact same type of thing. Can I identify regions of KT, CT space such that consumption is growing over time? Sure. If CT plus 1 is bigger than CT, then that means U prime of CT plus 1 is less than U prime of CT, right? Because the utility function is strictly concave. Well, that means U prime of CT over U prime of CT plus 1 has to be bigger than 1. But what is U prime of CT over U prime of CT plus 1 equal to? Well, here I'm going to appeal to equation 1. That is the Euler equation. U prime of CT over U prime of CT plus 1 is just 1 over 1 plus rho times F prime of KT plus 1 plus 1 minus delta. So 1 over 1 plus rho times F prime of KT plus 1 minus delta has to be bigger than 1. What we're looking for here is we're trying to derive a locus of combinations between KT and CT consistent with growing consumption. So let's see, if I keep working with this inequality, you get that F prime of KT plus 1 minus delta has to be bigger than 1 plus rho. Cancel, cancel. F prime of KT plus 1 has to be bigger than delta plus rho. Well, are we stuck? You guys remember what delta plus rho is equal to? That happens to be equal to the marginal product of capital at the steady state in this economy. That's one of the steady state conditions. So F prime of KT plus 1 has to be bigger than F prime of K star, which means that KT plus 1 has to be less than K star because F is strictly concave. And if KT plus 1 is less than K star, then I can appeal to equation 2 and write that as 1 over 1 plus N times F of KT plus 1 minus delta KT minus CT minus K star has to be less than 0. And if I turn around and express consumption then as an inequality over values of the capital stock, you will get that CT has to be bigger than F of KT plus 1 minus delta KT minus 1 plus N K star. This defines a locus of combinations between CT and KT consistent with stable consumption over time. For instance, if KT is equal to 0, then what's that value of consumption equal to? It's negative 1 plus N K star. That's why I've drawn it here down in this lower quadrant of the set of axes here. What does this particular locus of points look like then? F plus 1 minus delta k minus a constant, right? Well, that's going to be strictly increasing. But eventually, as capital gets really big, the slope is going to converge to what? 1 minus delta. Because for k really large, f prime of k goes to 0. This is the ct plus 1 is equal to ct locus of points. Every combination of kt, ct that lies on this curve is one that is consistent with stable consumption over time. Any point above this locus, however, let's take a point up here where ct exceeds f plus 1 minus delta k minus 1 plus nk star, is a point at which consumption is growing over time, meaning that consumption is moving in this direction. Any point below is going to be one in which consumption is shrinking, moving in the opposite direction. Now, let me really quickly, as I run out of time, I don't want to stop in quite this point. And I'll pick up right here next time. Hopefully you guys see that this analysis essentially demarcates regions of KT, CT space into actually 4 separate regions. So here was the KT plus 1 is equal to KT locus of points. Again, all the K's and C's that are on this locus are consistent with the capital stock being stable. Here is the CT plus 1 is equal to CT locus. All the points KT and CT on this particular locus are consistent with consumption being stable over time. You'll notice then that our 2 loci split this quadrant into 4 regions. Let's call it region A, region B, region C, and region D. Points in region B are above both loci. And so that means the capital stock is declining and consumption is rising. So if you're at any point KT-CT in this region, the economy is going to be moving northwest. Any point in region D is one where consumption is falling, but capital is rising. So if you find yourself in region D, you're moving southeast. All points in region A, however, are below the K locus, but above the C locus, in which consumption is rising and so is capital. So you're moving northeast. Points in the C region are ones, because it's below the C locus, is where consumption is declining, but it's above the K locus. So the capital stock is also declining. So if you're at a point in region C, you're moving southwest. The intersection of these 2 loci is going to identify, of course, where the steady state is, because only this point is consistent with consumption not changing over time and capital not changing over time. Now, this phase diagram is going to have trajectories for capital and consumption that are moving like this and also like this. And each one of those infinite number of trajectories is fully consistent with equations 1 and 2. There is only one trajectory, however, you can guess already, that is going to magically converge to the steady state. So that if you're down here, you're going to converge monotonically up towards the capital stock. If you're over here, you're going to converge monotonically down towards the steady state. This line here, this one-dimensional manifold in KC space, is the saddle path. And what we're going to talk about on Wednesday is how the saddle path is unique and why, for some given arbitrary amount of capital, consumption must jump up to the saddle path in the initial period in order to satisfy the lifetime budget constraint, that is the transversality condition. Once we get to that point, then consumption and capital evolve over time according to the Euler equation all the way to the steady state. That's what a phase diagram looks like. And if you want to analyze how exogenous changes affect the steady state in the Ramsey model graphically, you do so through a phase diagram, right? How does an increase or a decrease in the discount rate affect the steady state? Well, it's going to alter the position of these two locus of points and therefore change the steady state. But importantly, on the phase diagram, we can see how the saddle path shifts, and therefore we can see exactly how the economy transitions from the old steady state to the new one. Will it jump up or jump down to the new saddle path? Will consumption and capital converge up or down? We do that by analyzing the phase diagram. And I'm over my time limit, but that's what we're going to do in the next class. So the first half of the class, we're going to talk a bit more specifically about this picture. And in particular, why the steady state value of capital I've drawn less than the golden rule, okay? That's this so-called modified golden rule that I've alluded to a little bit in the past. And we'll discuss kind of intuitively why there should be only one possible trajectory here that leads to the steady state. And then what we'll do is we'll start a formal proof of the existence and uniqueness of this thing. I think that will take us into a little bit of class on Monday. So that's looking like when we'll finish it. So, but you guys that should give you enough time to settle all of your affairs for the exam on Friday then, okay? All right, we're almost done with this stuff. Just a little bit more to go.